Welcome back to another Info Index video. Today we will be talking about dynamic programming, which is a technique used to solve computer context problems, and we will also talk about how to use it. To start, consider the following question. Imagine if you were asked to compute the third Fibonacci number. This seems like a simple problem because you have most likely memorized the first few terms of the Fibonacci sequence, which is 1, 1, 2, 3, 5, 8, and so on. So you would immediately know what the third Fibonacci number is, and that would be 2. However, let's say I asked you to compute the nth Fibonacci number, where n can go up to 100. How would you go about calculating it? The most efficient and quite common way to calculate high Fibonacci numbers is to simply construct the Fibonacci sequence. You start with the first few terms, then add additional terms using the definition of the Fibonacci sequence. Every term is the sum of the two previous terms. In this problem, any given Fibonacci number represents a stepping stone. It represents a tool that is used to eventually obtain the final answer, which leads us to the first important idea in dynamic programming. Any Fibonacci number that we use along the way to obtain the 100th Fibonacci number is called a subproblem. This is called a subproblem because it is a smaller problem that we solve to eventually answer the original question of calculating the 100th Fibonacci number. We then use the pattern of the Fibonacci numbers to compute the final answer from all of these subproblems. We compute the final answer by starting from the beginning of the sequence and working our way upwards, and at the end, we will obtain the final answer, which is the final subproblem. Let's define the process in solving a problem using dynamic programming, using the Fibonacci number problem as an example. So first, we have to define the subproblem. Since you do not know the nth Fibonacci number directly, start by defining a subproblem that will help you to find the answer. In this case, the subproblem is, what is the ith Fibonacci number where I goes up to n? You can probably see that solving each subproblem, finding the ith Fibonacci number up to n, leads to the answer you are looking for, which is the nth Fibonacci number. The second thing we have to do is identify the base case. The base case is defined as a subproblem that takes a trivial amount of computing power to calculate. For example, you would probably be able to tell me the first 6 Fibonacci numbers without much thought. Let's assume for simplicity that you only knew the first 2 Fibonacci numbers. This would be your base case, which means you will only be able to tell me the first 2 Fibonacci numbers without calculating it yourself. You already know the answer to these. The third step is establishing the recursive relation. This is the trickiest part of an efficient dynamic programming solution. Here you need to determine the relation between consecutive subproblems. In this case, our work here is simple as we know the recursive relation between terms in a Fibonacci sequence from its definition. Fn equals Fn minus 1 plus Fn minus 2. Other dynamic programming problems may require more complex recursive relations. And finally, we compute the answer using our previous subproblems. Now that we have defined our goals for dynamic programming, let's use it to calculate the 10th Fibonacci number. So we don't know the 10th Fibonacci number, but I know that the first 2 numbers are 1 and 1. I know that any Fibonacci number is the sum of the 2 previous numbers, so that is my recurrence relation. Then the third number is 1 plus 1, which is 2. Fourth is 1 plus 2. 5 is 2 plus 3. 6 is 3 plus 5. 7th is 5 plus 8, and so on. And finally, we have that the 10th Fibonacci number is 55. Notice that at each stage, I'm only computing the answer to each subproblem. This is because each subproblem is usually much more computationally efficient to calculate. Using dynamic programming, I have found the solution much more efficiently than other methods. Now to extend the ideas of dynamic programming we just learned, let's look at the Canadian Computing Competition's 2007 contest, Junior Problem 5. The problem is described as follows. A truck driver is planning to drive along the Trans-Canada Highway from Vancouver to St. John's, a distance of 7,000 kilometers, stopping each night at a motel. The driver has been provided with a list of locations of eligible motels, with the respective distance of each motel measured in kilometers from the starting point in Vancouver. Some of the motel locations are, as listed below, but more motel locations may be added just before the trip begins. Determine if it is possible to complete the journey if the driver travels a minimum distance of A kilometers per day, the law sets a maximum distance of B kilometers per day, and each night the driver must stay at an eligible motel from the above list or the additional locations. The driver is interested in different options when making the trip, and you are to write a program to calculate how many different options there are. Here are the details of the input. You are given two integers, a and b, both of which are integers in the inclusive range 1 and 7,000. This represents the minimum and maximum speed that the driver has to travel each day. And more locations may also be added, and each additional location is in the exclusive range 1 and 7,000. So for the output specification, you should output the number of different ways the driver can choose the motels to make the trip under the given constraints. Now I will begin to analyze this problem. So, first, it is important to note that the driver cannot move backwards during any given trip. If the driver could move backwards, they can move indefinitely between two motels, and that would result in an infinite number of different paths. Also, it is important to note that the driver may or may not be able to reach the end if they must travel at least A kilometers per day and at most B kilometers per day, in which case the number of different paths to the end would be 0. First, let's compare and contrast dynamic programming with a simpler way to solve this problem, brute force. The brute force method is a problem-solving method that involves testing every possible case or configuration of a problem. So here we would solve this problem by looping through every possible configuration of hotels and determining if each configuration is a valid path for the driver, since the driver must travel at least 8 kilometers and at most B kilometers per day. So at the end, we just total up the number of valid configurations, and that number would be equal to the number of different paths from Vancouver to St. John's. However, in the input, up to 20 additional motels may be added. And since we already have 12 motels, the total number of configurations is 2 to the 32, since each motel can be either enabled or disabled. This will be way too many configurations, and our program will be way too slow. We need a more efficient method, and dynamic programming can help us achieve it. Let's start by defining the subproblem. To begin, let's consider all locations in order. More particularly, focus on the number of different paths from the start to a specific location. Our goal is to calculate the number of paths to each location, with the goal of calculating the number of different paths to the end. So our subproblem would be defined as the number of different paths to get to a particular location, starting from the beginning. Our end goal is to find the number of different paths from the start to the end, subject to the constraints of traveling at least A and at most B kilometers per day. Notice here that the number of paths from the start to the start is, unsurprisingly, 1. This is our base case. We do not need to use any other resource to determine the number of ways from the beginning to the beginning. We will now define a recurrence relation, which will relate the subproblems together. The recurrence relation can be very different depending on the dynamic programming problem, but one thing that it always needs is to utilize the answers to previous subproblems. As such, we are looking for a way to utilize what we already know, which is some collections of numbers representing the number of paths to locations that we already calculated, to calculate the next subproblem, which is the number of paths to a further location that has not been calculated yet. Alright, let's begin. So at location 0, the driver is already here, so unsurprisingly, the number of different paths over here is 1. Now let's look at the location 3. So the driver can go to location 3 by starting from any previous node. So in this case, the only previous node is 0. All we have to do is check if the driver can get here using the constraints of traveling at least 3 kilometers and at most 5 kilometers. We see that 3 is indeed in the range, so the driver can come over here. In this case, the number of different paths to get to 3 is just the sum of all of the previous nodes that can get to that node using these constraints. So the number of different paths to node 3 is 1. Now let's see the number of different paths to get to 4. Notice that we can't find this number directly. However, we do know the number of different ways to get to 0 and the number of ways to get to 3. All we have to do is check that we can get to 4 using these nodes, meaning that from 0 or 3, we need to be able to get to 4. From 0, it is clear that we can get to 4 by traveling 4 kilometers because it is in the range. However, at node 3, we cannot travel to node 4 directly because we'd be traveling too little. So the number of different paths to get to 4 is just the number of ways to get to 0, which is 1. Let's continue this pattern. So at node 5, we can get there from node 0 by traveling 5 kilometers. However, at nodes 3 and 4, we cannot travel to node 5 because they are too close together. So the number of ways to travel to node 5 is 1. For node 6, we cannot travel directly from node 0. However, we can travel directly to node 6 using node 3 only. Therefore, the number of ways to travel to node 6 is also 1. Now we are ready to determine our final answer, the number of different paths to get from 0 to 9. So we already have all these subproblems, which is the number of different paths to get from each node before 9. We will use this to calculate the number of different paths to get to 9. Look at each previous node. We will check if it is possible to get from the previous node to 9. At node 0 and node 3, node 9 is too far away because we can only travel a maximum of 5 kilometers per day. However, nodes 4, 5, and 6 are all close enough to get to 9 that we can get there directly, because from 4 you could travel 5 kilometers to 9, and from 5 you could travel 4 kilometers to 9. From 6 you could travel 3 kilometers to 9. Therefore, all 3 of these nodes can travel to 9. Look at how many different paths there are to get from 4, 5, and 6. We simply add up all of these different numbers to get the number of different paths to get to 9. So finally, we have that our final answer is there are 3 different paths to get from node 0 to node 9. So what I just showed here is a good example of how dynamic programming is applied to solve a Canadian computing competition problem. Our solution is much more effective because it will only take up to n squared time, where n is the number of locations. This is much better than the previous brute force method. There is a maximum of 32 locations specified in the problem. With brute force, we need at most 2 to the 32, which is 4 billion operations, while with dynamic programming, we need at most 32 squared, which is 1024 operations. Stay tuned for more videos about dynamic programming.